on this first picture, we're having so AND and OR constructing an AND. Okay, so A and A bar, B and B bar. That would A and B would go to the AND, the bars go to the OR, and eventually flipping the wires at the end, it would create an AND and an AND. So an AND and its bar, and that is what we're looking for, because with that we can construct all logic. So all logic and virtually calculus and anything else we want. Now this is, of course, for the OR and the AND. Right now we need transistors to make them. On this picture you can see that an AND and OR can be reduced to wires, and that wires could be reduced to pins that having same number, so groups of pins. And so the idea is to eventually the OR and the AND that you can see made with wires there, well, you have to send a signal at an end, and eventually if it returns to the other end, then it is a 1. If it doesn't, then it is a 0. And that's the entire idea here. So you send a signal, and it depends on where it returns. So this is a picture that shows how to have, for example, an addition of two numbers with 2 digits that gives a number with 3 digits to logic. This is another example where you're having an alarm system, and well, an alarm system would remember its previous state. So if you open the door, the siren would ignite, but when you shut it down, the siren would keep on. And so this is having it reduced to wires with transistors. So not only wires but also transistors, or groups of pins, I mean. But still requires transistors because it sends back inputs to the outputs, and that is the current and capacity. I mean, where we could evolve a bit more or add something. So it's like you send this from the output, you send a signal, it returns to the output. I mean, you send it to the inputs and it returns. But if you return, but if you get the outputs connected back to the inputs, it doesn't function unless you use transistors, and that's the way how